Just unmute yourself, throw it out there. Okay, so number 5, you're given that a rectangular box is designed to have a square base and an open top. Okay, so I'm gonna do my very best to draw a picture. Here, we'll make it a brown box, like a cardboard box. So rectangular box, whoops. That's gonna be one side of it. And then square base. Okay, so since this box has a square base, that means that the length and the width of the base are going to be the same. So you can use whatever variable you want to name the length and the width. I'm going to call the length and the width x. Those quantities x. And then we also have the height of the box is another characteristic about the box, right? And you can use h, or I'm going to use y. Okay, so y represents the height, x represents the length and the width. And the next sentence in number 5 says that the volume is 864 cubic inches. Okay, so the volume, which volume is length times width times height for a box or a rectangular prism, right? Is 864 cubic inches. Well, for our picture, our length and width are both x. So we would have our volume of 864 is equal to x times the height, which is y. So that can also be written as x squared times y. Now, this is all just given information. I haven't gotten to the part yet where I'm told what I'm trying to optimize. This is just based on my picture and the fact that the volume of the box has to be 864 cubic inches. Okay. So part A asks, what dimensions will give a minimum surface area? So that means that we are trying to minimize the surface area of the box. Now, part A isn't asking for the minimum surface area. I believe part B does ask for that. But part A is asking us for the dimensions that would minimize surface area, but we're still minimizing surface area. That's the quantity that we are trying to optimize. And in this case, minimize. So since we know we're trying to minimize surface area, we need a surface area equation. Okay, the equation that we have above that was for volume, right, ends up actually being our secondary equation or a secondary equation in this situation because the quantity that we are trying to optimize is surface area. Now, one note, it's really common that I see people use SA to represent surface area, and I wouldn't necessarily take off for that, but you want to kind of choose one letter to represent a quantity, right? Like usually when we see multiple letters next to each other, we think of those as separate variables and like two variables being multiplied by each other. So like to represent surface area, I would use either like S or you could use A, it's up to you. I'm going to use S if everyone's okay with that. And now I need to come up with the equation that would represent the surface area of this box. This box that does not have a top, but it has a square base. And the surface area is just going to be the sum of the areas of all the sides. So I'm going to go piece by piece and figure out how I would calculate the area of each side, starting with the base. So since the base is square, right, the area of the base would be x times x, or x squared. And then if I focus on just one of the sides, and I realize some of you guys could probably do this like instantly and just come up without having to think piece by piece, and that's wonderful. But if you need to piece it apart, especially when you're first starting with these problems, that's fine too. So the area of like just that side, the front of the box, the way that I have it drawn, would end up being x times y. And if you count, there are 1, 2, 3, 4 sides that would have an area of x times y. So if you're going piece by piece, you could be like, oh, okay, for that side, that would be x times y. And then for the other side, x times y. There's another x times y and one more, which that all would simplify to be x squared plus 4xy. Does anyone have any questions up to here? I know from the other class, what I was hearing in the emails was they were just getting stuck with how to set up the equation. So this is probably the hardest part. Okay, so we would want to take the derivative of our optimization equation, which is the equation for surface area. But we get stuck because surface area is being calculated in terms of x and y, which are different quantities. So we want surface area to be a function of either x or y, but not both. So that's where we can use our secondary equation, which we came up with from kind of the extra information that we had in the problem. So it doesn't matter which you solve for, but since y is raised to the first power and x is being raised to the second power in our secondary equation, it's going to be the most efficient to just solve for y. So then we can rewrite our surface area equation by replacing the y with 864 over x squared. And before we take the derivative, we want to simplify. So we would have x squared. This x can cancel with one of these x's. And then 4 times 864, I did this problem earlier, so I remember, is 3,456, 3,456 over x. Which, for taking the derivative using power rule, if you're visual like me, I have to rewrite it like this for me to be able to take the derivative and see how I would use power rule. So this is our optimization equation, right? These are both our optimization equations. It's just that this last one here is rewritten in its simplest form where we're ready to take the derivative. So we find s prime using power rule. So that would be 2x minus 3,456 times x to the negative second. Which, getting rid of the negative exponent, we'd move that x squared to the denominator. And if you guys remember from before break, our goal in taking the derivative here is to find critical values for our optimization equation, our optimization function. And to find critical values, we want to determine where the derivative is equal to 0 and where it's undefined. So if we have a fraction, a sum or difference with a fraction involved, it's often helpful to get a common denominator so that you can just think about setting the numerator of the derivative equal to 0 and solving, and then setting the denominator equal to 0 and solving. So we'll get our common denominator by multiplying the 2x by x squared over x squared, right? That version of 1. Okay, so that's just rewriting the derivative. Now we're at the point where we're ready to calculate our possible critical values. We're going to look at our possible critical values, and then we're going to look at what the constraints are. You could have already determined what the constraints are for your optimization equation. The order there doesn't really matter of what you do things. I like to find the possible critical values and then go, wait, which of these actually makes sense? And what are we going to use to prove that what the absolute max or the absolute min is? So setting the numerator equal to 0, and adding 3,456 to both sides and dividing by 2. I get x cubed equals to 1,728. And then taking the cube root, which is the same thing as raising 1,728 to the 1/3 power, we get 12. Okay, so we would want 12 to be a critical value. And then if we set the denominator equal to 0, right, we would get x equals to 0. So that's the other value that we want to be our critical value. And then we go up here, and actually right away I can see, because x is in the denominator in our optimization equation, right? X can't be equal to 0. So 0 is going to be thrown out right away. But if we go back to the picture and think about the situation, we're able to come up with a better description of the constraints here. So since x represents the length and the width, right, x can't be negative. And then based on this equation, we're going to go with x can't be 0 either. We don't know what the maximum value of x is. So we're not going to define x on a closed interval, or sorry, we're not going to define our optimization equation on a closed interval. But we do know that both x and y have to be greater than 0. So we can throw out 0 as a critical value, but we will want to use it on our analysis line. And we're going to use the first derivative test because for this particular situation, we can't come up with a closed interval that our optimization equation is defined on. So 0 is an endpoint of our interval, and 12 is a critical value. I've been blah, blah, blahing. So does anyone have any questions about anything up to this point? Okie dokie. So now I'm going to choose test values. And we're plugging those test values into the derivative. And I can actually see if we plugged 1 in, that would be 2 minus 3,456. So that would be a negative value, meaning the graph would be decreasing. And then when I plug 13 in, I get a positive value. So the graph changes to increasing. And this is where you might have to actually write down the statement that explains why at x equals to 12, there is an absolute minimum for our surface area function. And it's because the domain of our surface area equation is from 0 to infinity, and the graph goes from decreasing to increasing. So when x is equal to 12, that has to be our smallest value for the surface area. So my future AP kids, you might have to do the extra statement. You might not. I'm gonna actually check in with Mr. Green again. I'll tell you why I'm going to check with him when we do example 3. So I don't, for this class, need to see any other work than this. Like, this is enough justification for me. But before I write my sentence, I'm going to double check again what it is we're actually being asked to solve for in part A. So it says, what dimensions will give a minimum surface area? Well, when x is equal to 12, that's going to minimize the surface area. So that's the length and the width. We can see what the height has to be by going back up to our equation where y is solved for, up at the top here, and plugging 12 in for x there. So y would be equal to 864 divided by 12 squared, which I believe is 6. Okay, so then we could say something like to minimize the surface area of the box, the length and width must be 12 inches, and the height must be 6 inches. And I know it's inches because the volume we were given was cubic inches. So that's part A. Part B is asking for the actual surface area, what the minimum surface area is. So since you know what x and y are, you have options. Like, you can use the original equation that we wrote, so this one, and just plug in 12 and 6. Or you could just plug in 12 for x into our other surface area equation. It doesn't matter. It's kind of your preference. You've already done the work for either way. So plugging in, I'm going to just plug in 12 for x. Is it plus? Yeah. What is that? So I get 432. So 432, what would the units be for surface area?
Cubic inches.
The volume is cubic inches. Area would be
inches squared, right?
Inches squared.
inches squared or square inches. So we could say the minimum surface area of the box is 432 square inches or inches squared. Okay. Any remaining questions on number 5? Okay, so my plan is for us to do number 3 together. And then I'm going to let you guys go to work on the practice problems. Okay, are we ready? So example 3 is a really common, you guys remember how for related rates problems, I told you guys like the ladder problem, like every textbook has a sliding ladder problem for related rates. Every textbook has a box, an open top box problem. Super common, like you'll see number 1 and 3 are like this type of problem. And if you have a really good memory, you might even remember solving this type of problem in like pre-calc or algebra 2. Because this problem can actually be solved using algebra. But we are going to solve from a calculus perspective, and it's a lot, I think it's nicer solving from I think it's easier actually solving from a calculus perspective. Okay, so an open top box is made by cutting congruent squares of side length x from the corners of a 20 by 25 inch sheet of tin and bending up the sides. Normally in class, I do like a little, in person, I do like a little demo of this, but this will have to do. So let's say that that's the piece of tin. So this side would be 20 inches, 20 inches, 25, 25. And when we're cutting congruent squares out of each corner, the squares that are the same size, oh dear. Here, I could probably just copy that, huh? Can I copy it? No. Whatever. Pretend these squares are the same size. Close enough, okay? So, and we're also given that the squares have a side length of x. So each of these squares is x by x. And we're cutting each of these squares out of the corner of the tin so that then those tabs that are left on the side can be folded up. So like folding up along there, along there, along there, and along there. This is like pretty much what you do for gift boxes, right? Except for you usually, instead of cutting the square out of the corner, you like fold in the corners. So once you do fold up the sides, your open top box might look something like this. Oops. Okay. And after we've folded up the sides, the height of our box will end up being X. But what would our length and our width of our box be? Does anyone have any ideas? For what our length and our width might be? So we've cut the squares out of the corners. And we've folded up the sides. The height of the box will be X, so the same as the side length of each of those squares that we cut out. What would the length of the box be, which would be the longer side? Is anything popping into anyone's head? It's okay if it's not correct. Okay, so if we're cutting a distance of X into the length of the piece of tin, which is 25 inches long, I cut one square out. That length of 25 inches has lost X inches. And then I cut the square out of the other side.
Is it 25 minus 2x?
Woo! Yes, it is. Thank you. 25 minus 2x for the length, which then what would the width be? Annika, do you want to say the width as well?
20 minus 2x?
Yes. Do we all see that, you guys? Right, because we're cutting X inches in on both sides. So we're going to take away 2x from the length and the width for our folded box. Okay. So the question is, how large would the squares be to make the box hold as much as possible? So the key here is to make the box hold as much as possible. So what quantity would we be trying to optimize if we want the box to hold as much as possible?
Volume.
Volume. And would we be trying to maximize or minimize the volume?
Maximize it.
Good, thank you, Will. So we want to maximize volume. Which means we need a volume equation. And we, in the last problem, right, we're reminded that volume is equal to length times width times height of a box or a rectangular prism. So in this case, we could do x times 20 minus 2x times 25 minus 2x. I put the height first in this case, but multiplication is commutative, so order doesn't matter for the factors, right? Now, we need to simplify our volume equation a little bit. The nice thing is, notice that volume is in terms of just x. So we actually don't need a secondary equation. We're not going to have to rewrite this equation using a secondary equation. This is just our optimization equation. It's nice when that happens. So to simplify, you can either completely multiply out these factors. So multiply out and combine like terms. You also have the option of just distributing the x into one of the factors. So like we could rewrite this as 20x minus 2x squared. And it doesn't matter which of the factors you distribute into, but you only distribute into one. And I'll tell you, a common mistake I see is when students go to multiply something like this out with 3 factors, they distribute the x to both of the factors. And remember that each of those factors represents a number. So like if you thought about having like 2 times 3 times 5, you wouldn't distribute the 2, like if you're multiplying that out in your head, you wouldn't distribute the 2 to the 3 and the 5. You would maybe do, oh, okay, 2 times 3 is 6. So then you have 6 times 5, and that's equal to 30. But it would be incorrect to think about distributing that 2 to 3 and 5. You multiply 2 of the factors together, and then you can think about multiplying by that third. So this is an option. We could also multiply out from here. I'm going to just use product rule because I think that looks a little bit easier, to be honest. So V prime, it's your preference though. So V prime would be the first factor times the derivative of the second factor, which is -2, plus the second factor times the derivative of the first. Now at this point, we do need to multiply everything out. So like we're gonna distribute the -2 in to rewrite our V prime. So is that -40x? I guess the one nice thing, if we had multiplied out already, that our derivative would already be simplified and ready to set equal to 0, but that's okay. 25 times 20 would be 500, right? And then, oops, minus 4x would be minus 100x. And then we would have minus 40x plus 8x squared. And combining like terms, that would be 12x squared minus 180x plus 500. So that's V prime, simplified. I'm going to pause for a second. Does anyone have any questions? So since our optimization equation is a polynomial and our derivative is a polynomial, we can really just think about setting our derivative equal to 0. And this is a quadratic. You guys have your different methods that you can try for solving a quadratic. Your foolproof method is going to be quadratic formula, right? Will work for solving any quadratic. There's a GCF. You could factor the GCF out and get rid of the GCF by dividing by whatever that is. Or we can just, it would work to go directly to the quadratic formula. So that's what I'm going to do because I think that's what you guys would do. So using our handy dandy quadratic formula, right? Negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so that represents two different values. That would be x equals to 180 plus the square root of 8,400. I was just making sure that wasn't a perfect square. Over 24. Or x equals to 180 minus the square root of 8,400 over 24. Okay, so these are our possible critical values. But before I decide like what my final critical values are, also what method we're going to use to like prove absolute max or absolute min, let's look at what the constraints of our optimization equation are. And again, this step could be done first. Like this could be done right after you come up with your optimization equation. For some reason, I always tend to forget to do that until I get to the point of the critical value. So that's just why I do it there. But you can come up with the constraints right away if that makes more sense to you. So let's think about this. X can't be negative. It represents a length. If X is 0, that means we just have the flat tin. And the volume would be 0. Now, there is a restriction on how large X could be, like how long X could be. I'm going to go with 0 volume is okay here because I can tell from this picture that we're going to have a restriction on how large X can be. So that means I'm setting myself up to have a continuous function on a closed interval, and extreme value theorem implications could apply. Now, here is where I'm going to check in with Mr. Green. Somebody from the class yesterday asked, well, could you technically use first derivative test always instead of using the table and the implications from extreme value theorem? And the simple answer is, it's not a simple answer, it's sort of. Like to me, you could technically use first derivative test, but you would still have to think about the constraints of your optimization equation, especially to give a rigorous enough explanation and answer in like a free response question for an AP exam. And maybe for your guys' future calculus classes, like college calculus classes. You can get the correct answer using the first derivative test always. It's just to really be rigorous enough, you have to give that extra explanation. And that's where I'm going to check with Mr. Green on what his thoughts are and what he knows about the AP exam, especially for my juniors, about whether that's okay. Or if your optimization equation can be defined on a closed interval if you really have to do that. I prefer that. Like when I look for whenever possible to define on a closed interval, that's what my suggestion is. But I will double check on that and get back to you. I'm waiting to hear back from him when he can talk. So I'm going to say that X has to be greater than or equal to 0. Do you guys have any thoughts on what like our limit for X could be? Or what it is? Like what's the largest X technically could be? Right? If you think about it, like cutting in the same length on each side, maybe think about the shorter side. If you're cutting X inches in on both sides, what's the most that X could be where you could be cutting? I feel like I should have Jeopardy music here. So the shorter side is 20 inches. If we're cutting X inches into each side, what's the most inches X could be?
19, right?
No, because remember, X has to be equal, right? You're cutting X inches into both sides.
Is it 8 or 10?
Is it what?
Is it like 8 or 10?
It's not 8, it is 10, but can you think of why it's 10?
Well, then you would have no side left.
Yeah, then it'd be 0.
Exactly. So like think of it this way. If X is 0, we have 0 volume because we just have our tin. Technically, we could cut squares out for values of X strictly greater than 0, but that are really, really tiny and it would be a ridiculous box. We can say that X is allowed to be 0, there's just 0 volume, and that X can be 10 at the most. It's just there would be 0 volume because if you're cutting X inches into each side, well, on the outside, for the way that I have the picture drawn, the shorter sides, we just end up cutting straight across, right? Our scissors would meet in the middle and we would just cut those sides off, which would also be 0 volume. And you could see that if you plug in 10, right? If you plug in 10, yeah, you would get 0, right? The second factor here would end up being 0. So that we can define on the closed interval, and we have our continuous function, meaning we can do the table, we're going to use that as our restriction. You technically could justify between 0 and 10, like X strictly greater than 0 and strictly less than 10. But then I guess you would want to use the first derivative test and just think of those as endpoints. The issue there is there are some problems, not this problem in particular, where an endpoint can be an absolute max or min. So it's just kind of being careful of that. But we're allowed to, and I don't know if you guys have a preference on this either, I prefer to be able to create the table when possible over doing the first derivative test. Also because the table right away gives me what the maximum or minimum quantity would be. versus first derivative test, you still have to plug into the optimization equation. So it's kind of like killing two birds with one stone to me, to use the table. Now, I don't know, I have a hard time understanding or wrapping my brain around what these values are that I have here. So I'm going to find the decimal approximation for each of these possible critical values to determine whether or not they're actually critical values for this situation. So I get 11.319, which is outside our interval, right? That's too big, too long. You can't cut that many inches into both sides of the tin. And then if we did 180 minus, we get approximately 3.681. So that will be our critical value on that interval. I'm going to give myself just an extra page here. So making the table, okay, and I have the endpoints. You should use the exact value for your critical value. And if you, let me move this over. If you don't want to type that yucky looking thing into your volume equation, you might want to store the value on your calculator. I can't remember if I've gone over how to store values with you guys, but like I have that value typed into my calculator right now. And then I'm hitting the stow button, which is right above the on button. So it says stow, there's like an arrow. And then I hit the alpha button, the green alpha button. And then I'm picking a letter that I want to store this value under. So you can pick a button, like if I hit the math button, that'll store it under A. You can store under a letter. So pick a letter. And then hit enter. And the reason you would want to do that is typing 180 minus the square root of 8,400 divided by 24 into our volume equation. Well, that's in, at least if you use this one, that's in 3 different places. That's yucky. So if you store, you can just type in 20. So here, I just stored. So I can type in 20 times A. I just hit alpha A. Oops. Sorry, I hit alpha and then the math button to call up A minus 2 times alpha A squared times 25 minus 2 times A. Okay. So I don't know if you guys are able to see that maybe, but that's a lot less complicated to type in. So I get approximately 820.528 for the volume at the critical value. You can think about plugging them in, but 0 volume for our endpoints. So that ends up being our absolute max. You guys, my juniors who, if you're taking AP, you might even need to say like by the extreme value theorem. Like that's the absolute maximum. But Mr. Green will instruct you on that. So that's our absolute maximum. The question, where am I looking? Is asking how large should the squares be to make the box hold as much as possible? Well, we also know what the dimensions of the squares would be, right? We can use the approximation in our sentence. So about 3.681 inches by 3.681 inches to maximize the volume. So I'm going to put approximately 3.681 inches by approximately 3.681 inches. Questions, you guys? So in your textbook, there's 3 problems that I've assigned.